Good day. Now the fun starts. We've looked at calculus and we looked at the factor theorem. We've looked at the remainder theorem. We also looked at limits, and now we get to first principles. I'm sure most of you are already asking, now what is first principles? This is the slope or the gradient of a linear function to a curve given as a derivative. This is called differentiation from first principles, also known as the delta method. It gives the instantaneous rate of change of y with respect to x. I'm quite sure most of us know the progression of the gradient, where we said it is delta y over delta x. Then we wrote it as the change in y over the change in x, still delta y over delta x, where we had the little triangle in front. Then we elaborated and said it's y2 minus y1 over x2 minus x1, or also commonly known as ya minus yb over xa minus xb. Then we went to the average gradient of a curved graph, and then we moved over to limits. Now, when we talk of these limits, we speak of it as the first principles of calculus. So we use differentiation, which means the derivative of the original function. And remember, function we used to label as f of x. F of x referred to function. Now we have f dash of x, meaning the derivative of the function. Want to spend a little time on this notation here. This was the notation for the average gradient of a curve. This was the notation of the limitations that we could potentially face. And this is the full notation of first principles of calculus using differentiation. For all purposes, let's quickly recap. This section looks at calculus and differentiation from first principles. Differentiating a linear function, a straight line, has a constant gradient. In other words, the rate of change of y with respect to x is constant. You can take this rate of change anywhere on this graph. It would give you the exact same amount every time. Differentiation from first principles of some simple curves, and we will use the function notation. Calculus has to do with rate of change of y with respect to x, measured at an instantaneous point on a curved graph. Let's quickly look at a few. Here we have four different parabolas. I've drawn a tangent to the graph at this point, and this slope of this tangent won't be the same as the slope as this tangent at a different point. So anywhere on this graph, the slope of this tangent will change if it is a tangent to this particular graph. And you can see for each and every one of them, my slope would be different according to the point of intersection. Let's look quickly at hyperbolas. If I look at this hyperbola, there is a tangent. So the slope of this tangent compared to this tangent won't be the same. Although it's the same graph, the intersection is at two different points, so the slope won't be the same. If I take the same graph, but I go at point F, at point F, it will render a different slope from that slope meeting at point H. If I look at an exponential function, if I have a tangent to that function at any of these points, the slope will be different according to the point of intersection. For now, we will focus on first principles and stick only to that, and later on we will go to the equation of the tangent to that function using differentiation, not necessarily from first principles, but another form of differentiation. For now, we focus on the rate of change. So, if I have 2 points and a line is drawn, that particular line will have a gradient. And if those points come closer to each other, the gradient will change, or the gradient, the distance between the two x values will decrease, and the slope of that line will change according to the information given. If the points come closer to each other constantly, they will have the same gradient all along. We look at a few slides and see how it changes. Look at that point, it changes ever so slightly, and then later on when they get to a point where h becomes 0, as the h value, that distance that we were working with, as that distance tends to 0, it will become a tangent to the original function. So we go to the first sum. We will calculate the derivative of this particular function. So this function is f of x is equal to 2. So wherever x is, I will substitute x plus h. We've done this in limits, so now we continue. There is no x's to substitute, so f of x plus h will be 2 as well. We know the limit equation already, we're familiar with that. The only part that we add is the derivative of the function is equal to the limit of function minus the derivative of that function over h as h tends to 0. So, we have 2 minus 2. That will politely cancel out and give me 0 on top. So 0 over h, and I know if 0 is divided by any number, my answer is 0. So the limit of h as h tends to 0 in this case will be 0. If I look at the second one, the function of x is equal to 3x. Now I need to find f of x plus h. F of x plus h will be wherever x is, it needs to be substituted with x plus h. What I do now is I expand, I get 3x plus 3h. So that is the value of this in my equation. So now I say the derivative of the function is the limit of this minus that. And I will substitute this value in there and that value in there. Alright? I find that 3x will cancel out 3x. I'm left with 3h over h. H will cancel out h. I'm left with 3. So there's no h to substitute. So my answer is 3. The next one is x squared. So f of x plus h will be x plus h squared. So this part needs to be expanded. So this is x plus h multiplied with x plus h. And according to Pascal, I will get an answer of 1 to 1. So x squared plus 2xh plus h squared. This is substituted in the place of f of x plus h. Now I'm going to subtract from there x squared. If f of x is a single term, I will write it as follows. But if it's more than a single term, like a 2 term or a 3 term, then I will put a bracket first, and then I will substitute in there, because this negative sign will impact on each and every one of those terms inside the bracket. So I simplify, I get 2x plus h into h, which is my common factor. Look there, h is a common factor. I take out h, and h will cancel out h, and I'm left with 2x plus h. Now I'm substituting the value of the limit in the place of h. And the moment that I substitute the limitation, my limit notation disappears. So I'm left with 2. I'd like you to press pause now and try to do number 4 on your own. I trust that your answer looks like that. And now you can try to do the ones in your textbook. And I trust and know that you will have much success.